you're taking out the tests, and then if you don't get a B, then you're gonna retake the entrance exam thing?
No,
Or you
I
have
don't think that's an option at this point. If I'm looking like I'm not gonna get a B in it, I'll drop it. And then figure out something else that I can't afford a C right now, but a C wouldn't help. Wouldn't get rid of you know.
It would just make the GPA lower.
Exactly. It made my GPA lower and not match requirement, but this class is hard.
Yeah.
It's very hard. I'm not gonna lie, this is by far the hardest class I've ever taken.
Really? Even as an undergrad?
Yes. Especially as undergrad.
Oh, your undergrad must be not bad. Like, is
Have you ever
it?
taken a class?
No, but like inorganic was pretty tough.
It's just a lot of stuff.
Um,
The way he tests on like very small particulars of understanding of anything that he may have said / be in the book.
oh, so it's pretty much a crapshoot.
Like,
So like if you
it's a lot of
didn't
stuff.
study that one particular subject, then you're SOL.
Well, we'll find out. That's what I've heard. And I've seen it. It's very rough. Oh, whatever. You should take this one.
No, I'm gonna take the 660.
That's what I want to do now. It's not offered to us.
And you want to graduate, but if you want to graduate,
How are you?
good. How about you?
Good, thank you.
Are you enjoying the snow?
Absolutely.
Oh, it was terrible when I walked to the bus this morning.
It was hard.
Just right in the face.
A lot of snow. A lot of
I
wind.
enjoyed it, driving it. It's completely different feeling compared to
Oh yeah,
dry road.
drifting. Holla at your boy. I love drifting. Pull that e-brake, do a little turn. Yes.
Holla at your boy.
Yeah.
How about that?
So what are we doing?
We're finishing up the perturbation theory.
Yes. Are we waiting for Sam or it's his problems to come on to them?
I think it's his problems.
Okay.
You're recording it, aren't you?
Yes, but we will practice democracy again.
Oh.
Then I need to vote for him. So,
You don't have a tiebreaker.
I suggest we make another session of democracy by making presentations number 2 either next Tuesday and Thursday, and I suggest Tuesday in a week from now is better because a lot of you are going to conference and Thursday will be too short. Some prepare posters and presentations last night, so better to focus on class a little earlier.
When are these presentations?
I suggest
Tuesday or Thursday.
to make
Oh,
presentations
okay, I got you.
next.
I thought you were still talking about democracy.
Yes, because you will have an opportunity
Yeah, I got you.
to choose what you will be presenting. Okay. So application of perturbation, time independent perturbation theory. We will do it on today's 7th. 7 plus 7 is 14.
Oh, that's when I dropped.
And there is a list of about 9 topics, so just write your name near one of them. And the first 2 topics are very silly, so you need to have first and second choice. Maybe I will cover first 2 topics myself. What are they? So, topic number 1, second and third order perturbation theory. Second, degenerate perturbation theory. It's more class material. I would be happy to cover it myself. Third, connection between time-independent perturbation theory that we learned in class to MP Molar placid perturbation theory, which is available in quantum chemistry packages, just making connections with equations. The number 4 connection of between coupled cluster theory to perturbation theory. Someone is brave and reckless. And then number 5, perturbation imposed by octahedral field 2D orbitals. Matrix elements, diagonalization of matrix, and analysis of the solution. I can provide materials to cover this subject. Some of you see it as something very connected to your research. Number 6, perturbation theory for Stark effect, so splitting in electric field of like hydrogen-like atom. 7, perturbation theory for Zeeman effect, splitting in magnetic field. Number 8 is what I would choose myself. Perturbation theory for local dose in application to scanning tunneling microscopy, like hybridization between tip and substrate. And number 9, relativistic Darwin and spin orbit perturbations for heavy elements. So please. Last time you started from the first row, now you start from the last one, so that it is equal split of opportunities. So I noticed 3 of you to submit homeworks by email, and I think the rest of you are either bringing it in printed form right now or planning to submit it within like a few minutes. Right?
A few minutes. Uh-oh.
So it was homework 2. So MATLAB scan all perturbations, right? So I'm going to look on them, and I already saw 1, 2, 3 out of 6. No, 4. 4 out of 6. We'll briefly meet tomorrow at night for another session of digital planners. And
Do we only do one, or do we do first and second?
no, you do only one. You
write
do
the
second and first and second choice, just in case there is more than one volunteers for the same subject, so that there is a chance for conflict resolution. So it is QE132. So scientifically, what are we going to do? If this will be not visible, I can just handwrite and show from the projector. But then it will be projected on a small screen, so probably the board will be with limited visibility is better. So we are doing time-independent perturbation theory. Today we have to finish first order for energy and for wave function, and we'll do a brief review what we accomplished last time, and then we'll do about 3 steps. So there's really quick thing. 1, 2, 3. So we will take everything we collected last time for the first order and consider it in. We will consider change for energy and wave function of orbital number n. And as a first step, we will consider contributions only from those orbitals that only diagonal terms for perturbation. Then we will consider contribution for off-diagonal perturbations, and then we will use expansion in a basis. Unperturbed basis. So step number 1 will give the energies, and steps 2 and 3 will give correction to wave function. Yes?
Did you write 10 GW on here?
I'm not sure that it is. If you really want to do it, we can assign the whole 1 hour meeting for this. It's a little extended topic for 5 minutes.
I see 10 GW on here. I don't know if it was a legit option.
It is. Well, you can choose it as a second option.
But if I choose it, it's gotta be a 1 hour presentation.
We have a time, we almost experience.
Let me go and steal another pen from nearby room. Do not leave.
What was that?
I think there's a film on it, and I cleaned it. They don't have your great amazing spray.
They don't have my recipe.
No, they don't.
Come up with my recipe, or actually make it for them and sell it to them. That's a good idea. Does your board still work?
I think so.
It's not as great and amazing as commercial sprays.
No.
Commercial treatments.
But if I leave it on for like a week, you got your pink one back.
Yes. This is really bad to erase.
I think the board has a film on it.
Well,
That's
it
bad.
is erasable, but not as easy as dedicated dry erase markers. Okay. Rebel. What did we do last time? And generally, what are we doing? What is our goal? So we assume that we do have a solution of Schrödinger equation for a system, and then something is changing around so that Hamiltonian is perturbed. So there is a very small addition to the Hamiltonian, and we are inspecting how the small change in Hamiltonian is affecting the solution. The idea is that each problem can be split on solvable and unsolvable Hamiltonian. So the first part, which is big, is selected in such a way that it can be solved exactly, or, well, at least exactly in numerical sense, and then the second perturbation is small, and it will be small correction to the solution. So if we have change in Hamiltonian, then there is a change in wave function, and there is a change in energy. So we logically assume that there are two worlds. One where there are no perturbations, another when there is perturbation. And it is controlled by parameter lambda, that we are continuously changing from 0 to 1. There are more high level terms. And then we did plug in all this information into a Schrödinger equation. got expressions and then made the agreement that one can expand left and right part into series in powers of lambda, and then coefficients in front of equal terms should be equal. Then we did this trick 2 times. Once for Schrödinger equation and once for normalization. Schrödinger equation and one is for norm. Where did you stop when we finished a week ago?
We stopped getting the relationship of the perturbated wave function conjugated, and hopefully we can use that to use orthogonality.
Good. We got something like this as my memory can serve. Is it completely invisible?
No, there's just a glare.
It's visible. It's visible where it's
Oh,
not
that
visible.
one's fantastic.
Good. So this seems like the last equation we got, and I'm staying only with first order term because we need to do something new rather than repeat what we did last time. So, and from this, we assume that wave function no, we do not need to assume anything. The norm, this one conjugated, will be equal to this one. Should be, and we have
You need to switch your indexes. N and M, not N and N.
We're saying for the
For your
exact
wave
function, a
functions,
little chunk
it
of
needs
extra.
M and N.
Mm-mm.
Yes, that's what we did last time. It's with
It doesn't matter.
Well, for n equal m, this expansion is not very valuable. For different, if the indices are different, then the complete wave function will be orthogonal, even without perturbations. And the winning term only for diagonal elements, and we got that when we swap the order, add together it is equal 0, but one can deduce from this that each of them is equal 0 because by
It doesn't matter, right?
this bra and cat should maintain this property. When you take bra and cat and swap the order, nothing should change, right?
No, my question is the index. You have N.
And yes, diagonal.
Okay. Because I thought we were doing it because the off-diagonal elements might not give us 0.
We can return back to it
Okay.
later. But now we need only a situation when m equals n. And from these two equations, we can get that the when we add and subtract, we can see that this both equations will be valid only if it is 0. Right? When we scroll back, a couple of equations from last time, we are getting result of plugging these three equations into this one. And we got something for zeros order, first order, and second order. So let's bring back the expression for the first order. So it will be perturbed Hamiltonian to unperturbed wave function plus unperturbed Hamiltonian times perturbed wave function will be perturbed energy times unperturbed wave function plus unperturbed energy times perturbed wave function. Does this sound right? So if we add together order of perturbation in each term, it will be always 1. So 0 and 1 and all possible scores. Operator on the left, the eigen value on the right. 1 and 0, first order, 0 and 1, first order, 1 and 0, first, 0 and 1, first. So here is our plan. We are going to convolute this expression with zeroth order wave function bra from the left. And then we will consider two cases. One when k is equal n. So when the wave function we are convoluting with the is of the same index as the index of the wave function that we are looking to be perturbed, and then when they are of different indexes. And as a result, we are going to get corrections for energy and for wave function. Good? Any objections about the plan? Okay, let's call for mathematicians inside us and follow this plan. So steps. Step 1, step 2, step 3. It will be invisible in the space there. So psi of the zeroth order, and generally it's different index. Or under X we assume whatever variables are independent variables in the system. It doesn't mean that it is one-dimensional or continuous. So some of these terms will convert into unknown matrix element that depend on the perturbation. Some of them will be processed based on the fact that unperturbed wave function is an eigenstate of unperturbed Hamiltonian, and some of the convolutions will convert into delta function or will be processed according to the replacement of orthogonality relations for perturbations. So after we have done the convolution with bra from the left, there is a chance to get rid of the wave function and get an equation that will give us correction to the energy. So we are going to follow this line simplified, and then we will set up that m is equal to n. So here it will be matrix element of the perturbation in the basis of unperturbed wave function. Here we can consider the unperturbed Hamiltonian acting on the bra to the left. And with this trick, we can replace the operator to the eigenvalue. So we put here the index of our external wave function that we used as an auxiliary tool to convolution. And then this term will also become a delta function, right? Delta mn. So this term will be equal 1 if the indices coincide, and will be equal to 0 if they do not coincide. Any objection? Should this one is it normal? Or it induces suspicion? Okay. So we assume that the zeroth order unperturbed.
Is that 1, not 0?
One.
It's not.
Okay, yes. Thank you. Now I see why there was a suspicion.
It's 0, 1. That's over there.
And they this one is 0, this one is 1, And here, both are of the zeros order. So this is delta M.
But
Thank you
how
much.
do-
Yes?
How do you get the E naught? Because H naught Hamiltonian is what?
Or
No, just above here. How do you get this one? Oh,
so you can write down time independent Schrodinger equation for Bra and for K.
yeah, I was actually thinking because it changed to 0 to 1, and that's why.
So if we write Schrodinger equation for the Bra, then we can consider that operator
Okay.
is acting to the left. How did you call this term before? So let's go to the step number 1. So we are taking this expression only for the case when the wave function, artificial wave function that we used of the zeros order that we used for convolution has the same index as the original one. The same index. So then, first term will be just say n 0 perturbation psi 0 n. Diagonal element of the perturbation matrix L. The first order correction to wave function of the same index will be orthogonal to zeros order. And if we do have doubts, we can rederive it. So it this say 0 n say first n is equal 0. Doubts? I think it is boring if we just take the
No, we showed it over there.
we did show before. If you take the normalization for complete wave function and expand it in powers of lambda, one of the terms will come to this point. So here we will get 0. And here we place m equals n. Correction of energy. And here it is again the term. If we place the same index, it is the term that equals 0. what do we get? That if we do have small perturbation to Hamiltonian, small addition to Hamiltonian, then the energy of an eigenstate, and this all is for non-degenerate orbitals. Then the energy will have a correction which is equal to matrix, diagonal matrix element of the perturbation Hamiltonian. In many cases, it sounds very intuitive. See, it agrees with dimensionality, energy, matrix element of energy operator. But we got a little additional derivation of this conclusion. So we are done with step 1. So we got first order correction to energy. Now our plan is to get the correction to wave function, and our plan is to follow the same equation, but consider values of this auxiliary, the index of auxiliary wave function, which will be different from the original. I'm going to erase this panel and continue here.
Uh-oh.
Now I'm suffering the consequences.
Oh, that works.
Fine. It works.
So I'm going to rewrite this one. So what is our goal? What are we going to get? We are going to see what will be the changes in the wave function, in the orbital. How are we going to save this information? How are we going to record this information? Because we are trying to do everything so abstract. We didn't assume specific functional form of orbitals. We even do not specify are they continuous functions or expansion in discrete basis in methods. So it should be something very, very general. So the last idea, not mathematical idea, you can call it mathematical, that the correction to the wave function can be expanded in the basis of unperturbed wave functions. So if we need first order correction for wave function n, we can say that it will be expressed in terms of zeroth order. So it can be expressed in terms of the zeroth order wave function with unknown expansion coefficients. Unperturbed. Those are expansion coefficients. So this is actually step 3. So we are posing a question how to find an expression for these expansion coefficients.
I have a question.
Yes.
Where did L come from?
Arbitrary.
So the
How's it different than M?
there are 3 indices total. One for orbital where we start with, another auxiliary orbital that we multiply bra from the left, and third the running free index to count the orbitals used as an expansion basis.
Oh. L is something.
So that's the 0, 1, and then you're just going to bigger
So
values.
there is M, and N.
Okay.
And we will get rid of most of them. So, for original, for bless you, bless you, bless you,
Thank you.
and running index.
That was better.
So, what are we going to do mathematically? We are going to take this expansion and plug it in everywhere where we do have first order wave function. Right? Then, after this step, we will have only zeroth order wave functions for which the orthogonality relations are well defined. And we will be able to get rid of all wave functions and get an equation that will combine these expansion coefficients, energies, and matrix element. Good. So first term, good, that is not changed. So I plugged in this expansion into this term, and then by rewriting it, I placed the summation and index outside of this bracket. And then we have the convolution of the zeroth order wave functions. And on the right. We can save summation. Then convolution of unperturbed wave functions with index m and l. So we do have wave functions only in last term and last term before the equality sign on the left. Delta m, L. Delta m, L. Now we are going to use our decision about the plan. That in step 2, we assume that the index used for bra multiplication from the left is not equal to the original index of the orbital we started with. So m is not equal n. M is not equal n, which means this delta function will be 0. Other than that, nothing is changed in the equation. So we just drop this term. So the only thing that we need to complete is to perform a marriage between summation and delta function, between snake and a rabbit. So when they meet, the delta function and summation will disappear and indices will be assumed to be equal. Let me write it in 2 steps so that we do not lose anything. So I'm rewriting this. So now they are not equal to us. 0. You can skip this line, it will be technical. Zeroth order energy n. Summation, first order correction to wave function expansion times delta m. So if you perform the summation, then every time we meet L, it should be replaced to M. And here, every time we meet L, it should be replaced to M. So the delta function picks up only specific element. So the only element that will stay in this expression will be A1, n. And they look identical. Here, the element that will stay active will be A first order, M, comma, M. So let's see what happens. The first term stays unchanged. Zeros order wave functions for matrix element of perturbation to the Hamiltonian. Then we do have zeros order energy times A first order M, comma N. Right? Because of the summation. And on the right side, we will have zeros order energy for N. And out of expansion coefficients, we get the same M, comma N. So in these terms, the expansion coefficients are the same. And the energies up front are different. It looks like if we do one step more, this can be a good equation for the expansion coefficient, right? So we are going to consolidate this expansion coefficient terms on one side, matrix element on another, and then just find, just algebraically simplify it. So on one side, we have the matrix element, and on another side, we have first order correction for the orbital number n expanded in terms of matrix element M. And then we do have zeros order energy for orbital number n minus zeros order energy for orbital number m. Right? So I was just converting this expression by pulling one term from left to the right and putting the common factor out of brackets. So now we can divide both parts on this energy difference. and we actually get the answer. So it is the expression that corrects the wave function. We may want to, so we see that if the perturbing matrix element is non-zero, then any energies that are close in values, any orbitals of the similar energies contribute to the resulting correction. So it is kind of proof that resonance condition is important. Let's plug this one into our original expression. So first order correction is composed of zeroth order wave functions with coefficients that are proportional to this matrix element with resonance term in the denominator. And if you want wave function in general, we can tell that it is wave function of zeroth order that comes out from unperturbed Hamiltonian plus this term. So if this correction is insufficient, there is a way to add corrections of higher order. So we didn't complete everything that can be done for time independent perturbation theory, but it is the core material that opens a door to solve unsolvable equations, to solve the equations that can be solved exactly. So one can find approximate solution and then justify it by conversion, level of conversion to experiment. But if you are, like, suppose that you are scientist in the end of 20s, beginning of 30s, without computers, and you are a theorist, and you got a request to describe some process, and you are panicking because most of the problems are unsolvable. But this gives you a way to relieve pain. You find something, you identify part of a problem as a solvable, and then consider the rest of interactions as small perturbations, and then get approximate answer for both energy and wave functions. And the general statement from basic introductory quantum theory is that in case you know the set of orbitals, you can find expectation value of any observable for which you construct an iterator. So you find these wave functions, you get the observable of corresponding to your experiment, and find its expectation value to predict an outcome of an experiment. So this is very powerful technique that is allows to predict many experiments and is applicable in several situations for several systems. Where's the list? have forgotten to add one stuff that someone can vote for is we put it number 11. Van der Waals interaction between two hydrogen atoms. Like if you decide that it is your another choice, just send me an email. But this is another application, another famous application of the perturbation theory. So in the remaining time, like by now, we do have general idea, and we can either dig deeper for more precise corrections, or we can expand broader to different applications of this idea. So I will try to go both directions when we meet on Thursday, and you will go even further when we meet on Tuesday. Then on second Thursday from now, I'll summarize this chapter and start a new chapter, time-dependent perturbation theory, which is the core for any spectroscopy and interaction with light, or time-dependent magnetic field, and it's just different side of the perturbation theory that we will consider separate. Let me ask you if there are any questions. Yes? No? Okay, well, many thanks for attending the meeting. Let me announce the completion of the meeting number 9. I will announce the list of presenters for next Tuesday. Presentations will be expected by Monday night, so to give time for printing. And with now we are going offline, but I will stay here a couple of minutes just in case you have more questions.